In this video, I'll be sharing a little bit on floating point numbers, specifically what I've learned about them and how to understand them uh, in the IEEE 754 specification. I'll be only talking about positive numbers as that's the part that I currently understand a little bit better. But I think um, for the rest of the specification, we might perhaps explore that in a future video. I'll be using the 16-bit version of the 16-bit floating point number to explain and share my understanding of how floating point numbers are represented with binary. I chose 16-bit because 16-bit is smaller, so there's less bits to deal with compared to 32-bit as well as, of course, 64-bit. And 16-bit is the smallest official IEEE specification. We could use 8-bit, but 8-bit is typically just samples that are used in teaching and understanding. I wanted to instead use an actual specification IEEE floating point, um, so that it's a little bit more real, I guess. So to start off with, when we talk about 16 bits, there are 16 bits, but the question is how are these 16 bits interpreted by the computer, right? So there to start off with, it's a floating point number is broken up into three parts. Um, the first one is the sign bit. That just takes one bit. The second part is what we'll call the lowercase e bit. It's sort of the exponent bit as well, but there's a little bit exponent bits, but it's a little bit more involved than just being a simple exponent. So we'll get to it. And last one is f, or how I understand it as a fraction. So this is the third one. So in 16-bit floating point, sign bit takes one bit, the E part takes 5 bits, and the F or fraction part takes 10 bits. So for floating point numbers, there are actually, or at least positive floating point numbers, right? That we are concerned with in in this video. There are two different forms that I want to talk about. The first one is what's known as denormalized, and the second one is what's known as a normalized form. Um, I do not know the origin of these names, so yeah, that's that. But the two different uh, types of floating point numbers have slightly different behaviors, or rather, the bits are interpreted slightly differently depending on whether they are denormalized or normalized. So we'll start with the sign bit. Since we're talking about positive floating point numbers, the sign bit for all floating point numbers that we'll be talking about today is just zero. So I will backtrack a bit. I'm starting with denormalized numbers because denormalized numbers are the closest to zero. So if we start from zero and we increase the numbers in terms of uh, what do I call it? Greater than. um, Denormalized are the closest to zero, then past a certain point, they become normalized numbers. So the sign bit, the first bit is zero. So you can imagine, I'll just write an example up here, I guess. So this is the sign bit, right? Then E, for denormalized numbers, we'll start with zero, I guess. How to represent zero. Yeah, for zero, let's I guess I'll add a value. Um, I'll just write it down. Value of 0 here. Um, so the sign bit is 0. Then the value of e over here is for denormalized numbers. Yes, for denormalized numbers, the value of e is always all 0. Oh, let's use the red color. So that's 0 bit. Sorry, 5 bits. There's always 0. We'll come to the bias in a bit. Actually, right now. So for denormalized numbers, or backtrack, for floating point numbers, the bias is a predetermined number baked into the specification that is used to calculate the exponent of the floating point number. So I will get to it in a bit how we calculate the number and what that all means once we get to a number greater than 0. But for now, denormalized numbers have an exponent um, of 1, 1 minus the bias, which in this case is 15. So that is 14. And for f, because it's just 0, it's just 0 is just all zeros here. And n here is just the same value. We'll get to m in a bit once again we go to a number greater than 0. So I realize perhaps this example isn't so great, but at least we start to have an idea of what the numbers do. So let's go to the first smallest positive value of f16. For a denormalized number, the numbers which are closest to 0, again, so let's write down the value smallest positive. So the sign bit is again 0 because we are talking about positive number. Because it's a denormalized number, E here is all zeros again. This is just a property of denormalized numbers. And for the exponent, it's 1 minus E. 1 minus the bias for a denormalized number. So that is 1 minus 15, which is 14. And F here is 8, 9, 10, 1. This here is 0. This is a fraction, right? And how I've come to understand how to derive this fraction is rather straightforward, actually. So we have the numerator and we have the denominator. The numerator is simply this value here as a binary number. So this one is just 1. And the denominator is just, if we imagine f to be all ones. No, sorry. Yes, no. We count the number of bits, right? So this is 10 bits, right? We have 10 bits. So we do 2 to the power of 10, which is equal to 1024. So the fraction value here is converted into what is called mantissa. I'm not sure if I'm spelling it correctly. Which in this case, the smallest positive value is 1 over 1024. Now with the exponent and the mantissa, how do we calculate the smallest value of f? The smallest positive value of f equals F16, float 16 bits. Um, how we do that is actually these two are actually negative 14 because 1 minus 15 is negative 14. So the value here is 2 to the power of negative 14 times 1 over 1024, which in this case is roughly this number over here. Not going to try to pronounce that. But that's roughly how we derive uh, a positive number uh, from floating point, from reading the floating point uh, bits essentially, right? That is in a denormalized form. So if we go to here, the sign bit, so to my pen, sign bit, then you have E, which is 1, 2, 3, 4, 5, and you have F, which is 3, 4, 5, 6, 7, 8, 9, 1, 1. So this is the smallest positive floating point, 16-bit floating point number. Let's use another random example just to understand this denormalized form a little bit better. So 0 here, because it's denormalized, we have 5 zeros here. The exponent, again, is 2 to the negative 14. And let's say, I don't know, 0, 1, 0, 0, 1, and 1, 1, 0, 1, 0. Okay, so this fraction here is this 1, this is 2, 4, 8, 16, 32, 6, 4, 1, 2, 8, 2, 5, 6. If we add all of that together, 2, 5, 6, 32 is 2, 8. This is 6, 32, 2, 8, 8, 16, and 8, and 2. So this is 10, 16, 24, 24, 2, 10, 11, 11, 2, 3. So here the fraction is 314 over 1024, which means this value here is 2 to the negative 14 times, well, 314 over 1024. And that is for denormalized values. Next, we are going to talk about normalized value. So as you perhaps can tell already, sign bit is again 0 because the sign we are only talking about positive numbers. But for for normalized values, the value of E is between 0, 0, 0, 0, 1 and 1, 1, 1, 1, 0. If the last number is a 1, then the way this floating point number is interpreted is again different. So we are only going to talk about normalized values today. So the value of E for a normalized floating point number is between 1 and, well, 1 less than the greatest value of E. So in this example, I will use a value of E that is not 1, just to illustrate something different. Let's maybe 0, 0, 1, 0, 1, right? So 1, 2, 4, this is 5. Okay. For normalized numbers, instead of doing here, it's a different color, 1 minus bias for E, right? For normalized numbers, it is E minus bias. And that's the first difference. The second difference is that for F, for normalized numbers, I guess I can use blue for all the normalized numbers. For F, the normalized numbers have implied leading 1. I will get to what that means in a bit when we calculate the mantissa, but just keep that in mind for now. So we go back to the exponent. So if we do 5 minus 15, this is negative 10. So let me rewrite that, negative 10. So if we bring this over here, you can see 2 to the power of negative 14. So now it's 2 to the power of negative 10. For fraction, let's use the smallest one that we have first. So let's say 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. We calculate the mantissa value by first converting the fraction, similar to how we do so for a denormalized value. So this is 1 over 1024. But we add 1, which in this case is, well, just to make things clear, right? 1024 over 1024. So that means the mantissa value of a normalized value is the value of the fraction plus 1. So this is 1025. That means the value of this floating point, 16-bit floating point number, which is 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. It is 2 to the negative 10 times 1025 over 1024. That is how we calculate a normalized floating point number. Let's try a big one, just, why not? See what happens. So 1, 1, 1, 1, 0, the biggest possible E, that is still a normalized number. So this is 1, 2, 4, 4, 16. So this is 16, 24, 28, 30. 30 minus 15 is 15. That's very big. 2 to the power of 15. Might be able to calculate it. And let's use f of, let's just say all zeros, why not? Which means this is 1024 over 1024, right? So this is 2 to the 15 times, well, times 1. So 2 to the 15 is 2. 2 to the 1 is 2. 8, 16, 32, 64, 192, 16, 3, 8, 4, and 32, 7, 6, 8. So this should be 3276. So I just double checked my values and I think they are correct. So the floating point F16 uh, representation of the number 32768 is 0 1 1 1 1 0, then the rest are zeros. So this is essentially how a positive floating point number is derived uh, from the floating point representation of the number. There is a sign bit, there are exponent bits, which require some calculation, right? Involving the bias, whether it is a denormalized number or whether it's a normalized number, where denormalized numbers, the value of E is just all zeros. So the exponent, the value that you raise 2 to the power of is 1 minus the bias. And for normalized values, the exponent is derived from taking the value of E, which could be anywhere between 1 to the largest value of E minus 1. So when there are 5 bits, it's 1 1 1 1 0. You take that value, minus it by the bias to get the exponent, and you take 2 and raise it to the power of this exponent multiplied by the mantissa. And the mantissa is derived by taking the fraction itself. For denormalized numbers, the fraction I've shown up here, how I derived it, at least when I was trying to understand this, is the numerator is just the value, right? While the denominator is the number of bits, is 2 to the power of number of bits. So 10 bits, 2 to the power of 10 is 1024. And that's the mantissa value of a denormalized number. And to derive a denormalized, step back, for normalized numbers, similarly, get the fraction, same method, but we need to add 1, right? To get 1025 over 1024, which we compare these two. This is 1 over 1024. This is 1025 over 1024. This mantissa value here multiplied by 2 raised to the power of the exponent gives us the floating point value. And that is how we can derive floating point decimal values from the floating point representation. To extend this to F32 and F64, the main thing that we need to know is the number of bits for E, the number of bits for F, and what the bias is. From there, we can adjust our calculations accordingly and be able to derive the floating point, or rather the decimal value of a floating point representation, IEEE 754 floating point representation number. Basically, floating point to decimal number and how we calculate that in between. I hope the explanation of positive floating point numbers was useful to you. If you are learning computer science concepts, software concepts, how computers work, like myself, I hope this video, this short explanation of just a very small subset of floating point numbers has helped you understand it a little better. Explaining it in a video format has certainly helped me understand this concept better as well. So if you do like this kind of content, this is what I do plan on making even more of. You can see even more okay, these aren't really computer science books, but computer books. I have more behind that. I do plan to continue studying as well, continue learning. So as I do so, I will be sharing even more content in the hopes of helping someone else out there, helping you understand these concepts better as well, while I also reinforce my understanding while creating these kinds of videos. So if that's what you would like to see, do like the video, subscribe, and I'll catch you in the next one.